All right, let's get started. Good morning, everyone. Oh, it's getting worse. More energy, please. Good morning. That's much better. All right, so what are we doing today? We're doing lesson 35, section 10.5. We're going to look at conic sections. And I'm sure all of you have seen conic sections before, and the point of this lesson is to give you a little bit of refresher before you head into 261 when you take Calc 3, where you will be dealing with a lot of conic sections. Okay? So as a reminder, what conic sections are, these are the things that you would get if you were to slice a double cone in various different ways. So for example, in the leftmost picture here, we have a double cone. If I take a plane and I slice it through one of the cones, if I slice it this way, you notice we get a parabola out of it. If I take a plane and I slice it perpendicular to the vertical to the base or perpendicular to the axis, I get a circle. And at a slight angle, I can get an ellipse. If I take, again, a double cone, but I take the plane and I slice it vertically down, I can get a set of parabolas. So we got three kinds of shapes to look at. Parabola, ellipse, circle, same thing, and hyperbolas. Okay? So again, you've seen this before. This is just a review of these shapes. Let's start with parabola. So the definition of a parabola is a set of all points that are equidistant from a fixed point we call that point a focus and a fixed line. And we call that line a directrix. All right, so that's the definition of a parabola. And you might remember the equation of a parabola, but let's use that definition here and get that equation out. Let's see why that equation is the way it is. So let's consider a parabola that opens upward. With a vertex at the origin for simplicity. Now, once you understand how this equation comes out, you can adjust the equation for a different case. So we'll see how this thing works. All right? We're talking about a point here called a focus. Let's put the focus right here in red. And let's say it's sitting at the coordinate 0, p. In other words, it's at a distance p from the origin. The directrix is on the other side of the vertex at the same distance away. So it's not part of the parabola. So we treat it kind of like an asymptote. It's not exactly an asymptote, but it's the same idea here. It's a line that doesn't exist, but it's something that helps us guide the sketching and how we can get the equation out of it. It is also at a distance p away from the origin. And the equation, as you can see, is y is equal to negative p. All right, so then the parabola, we know what it looks like. Something like that, right? And a property, by definition of the way we get these points, is that if I choose any random point on the parabola, say right here, x comma y, then it has to be equal distant from the focus and to the vertex. We drop it perpendicular down. So on the picture I drew here, they don't look equal, but for a true parabola, these two must be equal. Let's call the one at the top D1 and call the one dropping perpendicular down as D2. And that's the vertex, right? Okay, now let's derive the equation for this shape here. The first distance here, very simple. If we use the distance formula, x minus 0 squared plus y minus p squared. And D2 is pretty simple, too. We know this portion right here is p. So then the portion above the x-axis is y, right? It's y high, and then p more below it. And to get the equation out of this, we simply set these two equal, and then write out the equation. So D1 is equal to D2. The algebra is not too difficult here. Square both sides. Oops. All right. So I square both sides. I got this thing here. Okay, let's continue with that line there. Let me write it here. Plus y minus p squared is y plus p, the whole thing squared. Okay, then we just expand these two things. And then combine everything to one side. Notice y squared will cancel. P squared will cancel. So if I leave x squared on the left and then kick this to the other side, I get 4py on the other side. All right, so this is the standard equation of the parabola whose vertex is on the origin and opens upward. All right, so this is an upward opening vertex at origin. And this is when p is positive. The way we drew that picture, we assumed positive p, since the vertex, since the focus is going upward toward the positive y direction. Now, if p is less than 0, then what happens to the shape? What changes? Look at the picture here. If p is 0, where's the focus? It will be below the focus will be below the origin, right? So this thing will be opening downward. All right? So that's the equation for upward, downward opening parabolas. Whichever way it opens is depending upon the sign of p. Now, we're not going to go through the algebra here, but if you interchange the two variables, write it as y squared is equal to 4px, then what you got here is a right or leftward opening parabola. Whose vertex is at origin again. And a positive p gives you a parabola that opens to the right, whereas a negative p gives you a parabola that opens to the left. Okay? All right, so you've seen this stuff before, right? You should have. Right? You should have seen this stuff before even you were allowed to take calculus. But if you forgot, here's a nice refresher. Okay, let's see what we can do with this equation then. Got this equation here, 9x squared plus 8y is equal to 0. And you can recognize this as a parabola because only one of these two is squared, right? In either of the two forms we saw earlier, only one of the two variables is square, either x or y. If they're both square, then we got a different shape, but only one square, then we have a parabola. So what remains here is to determine which way it opens, and then we can find out the three things pretty easily. So let's start by rearranging this equation just a little bit. If I leave the squared variable on its own side, like in the standard form, then I see I have negative 8 over 9 times y on the other side. Okay, so which way does this thing open? Down, right. Right, x is square, so we know we got up and down going on. A negative number here. Another way to see here is if we line it up next to the standard form here, then we see 4p is equal to 8 over 9. So that means p is equal to minus 2 over 9. So we have a negative p. Therefore, that's a downward opening parabola. Okay? All right, so just sketch it in. That's what it looks like. The focus is always inside the mouth of the parabola, right? So it's got to be over here at 0 for x and minus 2 over 9 for y. So that's my focus. Then the directrix is at the same distance, but on the other side of the vertex. So the point this thing goes through is 0, positive 2 over 9. And it's a horizontal line. So there they are, the focus and the directrix of the parabola here. The vertex is at the origin, right? So that one is obvious. Okay? And you might know some common applications of parabola. One of the ones that you see quite often is like a satellite dish. Right? If you build a satellite dish in the shape of a parabola, and you put a receiver at the focus, then all the rays that come into the dish will bounce off and go through the focus. And that will give you the strongest reception. And that's one application. Another application is a floodlight, a very strong spotlight, for example. Kind of like the headlight in your car. You want it to be focused and strong. So if you put a light bulb here and then build a shape of the enclosure in the shape of a parabola, then it'll get you that kind of focused light. Now, in reality, the shape of your car headlight is not exactly a parabola. It's a little bit more complicated, but it's based on the basic idea of a parabolic shape. Okay, questions on the parabola? Nope? Okay, that's a very simple shape. Let's look at the next one, the ellipse. So once again, the definition of an ellipse is a set of all points such that the sum of whose distances from two fixed points they're called the foci. Foci is the plural form of focus. If you say focuses, no one's going to complain, but people get the idea. But strictly speaking, it's foci. Is a constant. Okay? So here's my ellipse. Pretty good one, if I say. What do you think? Pretty good, huh? Whatever. Okay, so we need two foci. The foci is always on the longer axis. Let's put one right here and the other one right here. It's always along the longer, in other words, the major axis. The shorter one is called the minor axis. And let's say that they're sitting at negative C0 and positive C0. To find the equation of an ellipse, we pick a random point on the ellipse again. And we'll find the distance from both of these foci, right? So here's the first one. Here's the second one. Once again, I'll call them D1 and D2. Then, using the definition of the ellipse, we know D1 plus D2 is a constant. So let's write out what D1 and D2 are. Again, using the distance formula, D1 is x minus c squared plus y minus 0 squared. And then D2, x minus c squared plus y minus 0 squared. And we want this to be equal to a constant. For convenience, we're going to say the constant is equal to 2 times some other variable a. Okay, you can call the constant anything you want. You call it 2a, then it happens to be part of the shape. Okay, so the derivation of the equation is a little bit lengthy, and I'm not going to go through the entire thing. If you're interested in how the equation comes out, look at page 672. So I'll skip that. It's a little bit lengthy. It's not difficult. You just simply have to deal with squaring this thing twice to get rid of these radicals and then collect the equation. Okay? And if you actually went through that at the end of the day, well, not a day, but at the end of the process, you end up getting this equation here. Anyone remember what A stands for? Where would A be on this picture of the ellipse? What is A, in other words? So C is the distance of the foci from the center. What about A? Yeah. So right here. Yeah, that's right. So this point right here, that's A0. And this here is negative A0. And the ends of the major axis are called vertices. That's the plural of vertex. It's kind of like a parabola, but kind of doubled up, right? You have focus, vertex, another one, mirror shape on the other one. So you can think of it as two parabolas kind of merged together in a special way, and you get this. And usually we define this a squared minus c squared as b squared. And most often you will see it this way. And customarily, we let A be bigger than B. All right, so now what do you think B is then? Where would that, what would B represent on the picture of my ellipse? Take a guess if you forgot. Yeah. The what? There are no asymptotes here. Yeah. Between here and here? Good guess, but not quite. Yeah. Right. The ends of the minor. Right. Good. So right, this one right here would be 0, comma B. And this one right here would be 0, comma, negative b. So b tells you how long the minor axis is. So A usually is also referred to as the semi-major axis, because A tells you how long half the major axis is, so semi-major. And B is the semi-minor. Right? Half of the minor. So the length of the major is 2A. A by itself is half of that. The length of the minor is 2B, and half of it is B. Okay, so this gives you an equation for an ellipse that's longer along the x-axis. For an ellipse that's longer along the y-axis, something like that. And once again, the foci always sit along the major axis. And to get the equation for this kind of shape, you simply take the previous equation and interchange x and y. Because what happens here is this is the same shape, but kind of rotated. If you simply relabel your axes, then you got the shape you want here, right? So the equation would be x squared over b squared plus y squared over a squared equal to 1. And then the relationship between A, B, and C is the same. So this gives you a shape that's longer along the y-axis. So basically what you do here, the first thing you do is identify which one you got. And you look for the bigger of the two numbers. If the bigger number is under y, it's longer along y. If the bigger number is under x, it's longer along the x-axis. Okay, let's try a very simple one here. X squared over 25 plus y squared over 9 is equal to 1. And like I just said, you look for the bigger of the two numbers and see which one it is under. The bigger of the two, 25, is under x squared, so we know we have a shape like the one we saw on the previous slide, something like that. the major axis is along the x-axis. Okay, now let's identify what A and B are. Those are pretty simple. We see right away A is equal to 5. So that tells me half of the major axis is 5 units long. And B squared is 9, so therefore B is 3. That tells me that half of the minor axis is 3. And then lastly, let's identify where the foci are. The foci are at distance C from the center. So you can see it's got to be less than A, right? So we're going to use a relationship we saw earlier. B squared is equal to A squared minus C squared. So that tells me my C squared has got to be 16. And therefore, the foci are at distance 4 from the center. So for this ellipse, the foci are at minus 4, 0, and 4, 0. And the vertices are at minus 5, 0, 5, 0. Now, if the two numbers switch places, then you got exactly the same thing, but rotated 90 degrees, right? Because all that's going on there is interchanging the rows of x and y. Questions on this? Yeah. Angle, we're not going to consider that because if you encounter stuff like that in practice, usually what people do is they redefine the axes and then work out the relation there and then worry about what the new definition do to the original x and y. So you leave the equation here simple and then deal with the consequence when you redefine it. Yeah.
Do we ever see it where the distance is sum to some constant is not 1?
That's not 1. The right-hand side here?
Yeah.
Yes. If it's in the standard form, the right-hand side is always 1. So if you're given an equation whose right side is not 1, you divide whatever you need to make it a 1, and then you look at what these things are. Okay? So that's a good point here. This is always 1 in the standard form. So if I had like a 4 here, I would divide everything by 4 and then look at what A and B are after I did that. So we're not going to look at the ellipse that's slanted. We will look at what happens when the center is not sitting on the origin. And let's say, for example, the center is at h comma k. Then And then let's suppose that the major axis is on the x-axis. So we will start with this equation here, and then take into account the shift in the center. And it works just like a circle. Right? For a circle, you know if the center is not at the origin, then instead of x squared plus y squared, you have x minus h squared and y minus k squared. Same thing here. That's all you have to do. Make sure, once you identify where the center is, then you shift it. Okay? Okay, let's look at the last shape here, the hyperbola. Now, definition of hyperbola, it's very similar to ellipse, actually. Again, set of all points such that the difference, instead of the sum, the difference of whose distances from two fixed points. They're also called the foci, is a constant. So very much like the ellipse, if you turn the sum in the ellipse case into a difference, then you get hyperbolas. So hyperbolas look something like this. There are two branches. One way to conceptually see what's going on here, you can think of it as you take the ellipse and turn it inside out. It's not exactly like that, because these are not elliptical shaped things. They're also not parabolic shaped. But conceptually, thinking of this as an ellipse turned inside out can help you to see why this kind of thing is happening when you change from a sum to a difference. The vertices are again at A away from the center. And just like for the parabola, the foci sit inside the hyperbolas. So they look like this. And once again, I'll skip the derivation. It's just like the ellipse case. And it's based on the same idea. We want the difference of the two distances to be a constant. Right? This thing has two branches. I can choose either branch to work with. If I choose the right branch, then I can see these two things. So derivation follows just like the ellipse. This time it's the difference between the two. Now there's a slight twist here. On the right branch, d1 is bigger than d2. On the left branch, d1 is smaller than d2. So the difference can be either positive or negative. So that constant is still 2a, but we need to account for the fact that this could be positive or negative. Okay, so after a little bit of algebra here, we end up getting this equation. Now this thing looks kind of like the ellipse case, except in the ellipse we have a squared minus c squared. And also in the ellipse we have a positive sign. Here we have a negative sign, and the places of these two things are switched. So we got this kind of equation for this shape here. Another difference here is that this quantity b doesn't show up anywhere on the hyperbola. B doesn't have any place to go on here. But b plays a role in defining how we can sketch it. So that's for the left-right case. For the other case here, once again, you interchange the rows of x and y to get the other case. Okay? And the hyperbolas also have some very, very interesting applications. I'll tell you one of them after we go through this example. Let's look at this one here. 16x squared minus 9y squared is equal to 144. So this is just like the ellipse case you were asking me earlier about when the right-hand side is now 1. So what you do when this is now 1, you divide everything out first to make it a 1. Right? You make the right-hand side a 1 by dividing 144. And then you deal with the consequences of that. And in this case, in the ellipse case, a squared is always the bigger number. But in the case of a hyperbola, a squared is the first denominator here. So A is equal to 3, and B is equal to 4. To sketch this thing, one very helpful way to sketch is to start with asymptotes. I'll show you what they look like. If I take the equation here, the equation I started with, solve for y, okay, so you take y over here, subtract 144 divided by 9 all the way through. So here y, when I take the square root, is plus or minus 16 over 9 x squared minus 16. And notice when x becomes very large positive or very large negative number. In other words, when x squared becomes very large, this minus 16 or plus or minus whatever make no difference in the end. So when this happens, y is more or less like plus or minus 4 over 3x. And when you sketch that, these are the asymptotes that envelope the two branches. All right? And we already identified that because x squared shows up first, this thing is going to open left and right. And A is equal to 3. So 3 distance left and right at the center, right here. These are where the vertices are. So the two branches have to live within this triangle and that triangle. Something like that. Oops. Finally, let's find out where the foci are. C squared is A squared plus B squared. And that's 25. So C is 5. So that's focus number 1. And here's the other focus. Okay, so one very useful application of this is pre-GPS days. When you're flying over the ocean, for example, you can't tell where you are. So what you do is you set up 2 radio stations broadcasting signals. And say your airplane's right here, you hear the difference between your time when you get from station 1 and 2, find the difference. If you know the difference is something, then you know you got to be either on one of these 2 branches. And that can help you narrow down where you are. So that was before GPS days, and they used that technique during World War I quite extensively. Okay, that's it for today. See you Friday.